for linear dependence, let's say we have two vectors, and all we're saying for linear independent is this situation where you have these two, and there's no way you're going to get u from v. There's no way v is going to end up at the end of u. There's no way. If it's 1, 2, -1, 0, it'll never get there. They're independent of each other. Same with in reverse. But if you have something like this where u is this vector and v is this vector, what can we say about u and v? Yeah, u can be described in terms of v, so we say they're dependent. U is dependent on v. Okay, so this first one, I think that drawing helps a little bit. Any list of vectors in the 2 space, r squared, which one of them is a 0. So if you have any list of them, if you have a vector v equal to 0, that means you can put that v with anything, right? Any direction, you can put a 0. So therefore, whenever there's a 0, it'll be dependent. Any two vectors are linearly dependent. If one of them is a multiple of the other, we showed that. Perfect. Linear dependent. This is the one I think is interesting. Any list of 3 or more vectors in our dimension 2 is linearly dependent. So I have these two. Let's make it u and v. Usually those are linearly independent. Yeah. What if I throw in a w? Oop, I don't want to go that direction. No. What happens when you put that w in there? Turn to your neighbor, see if you can tell me why these are not independent anymore. We conclude that any list of 3 or more vectors in R2 are going to be dependent. Isn't that interesting? Does that make sense? Turn to your neighbor and explain that in your own words. Go. So now we're going to go into 3 space, and in 3 space, you have any list of vectors R3. If one of them's a 0, is that going to be, are you going to be able to use that to describe any other ones? Yeah. So that automatically resets it to being dependent. Because any vector can be written in terms of the 0 vector, so you can throw in it, and because it does, it's going to be a multiple.
So is it not any list of vectors that has 0 anywhere in it?
Any list of vectors, if one of them or more is 0, then it's dependent.
Every element is 0. Yeah.
Doesn't have to be right. And then for this one, now remember, we're talking about dependence. If one of them is 0, they're going to be dependent. Any 3 vectors, if one of them is a multiple of 2, well, that's the same as this, right? You know, that's nothing new for that. So these two are the same for both 2 and 3. Any 3 vectors, u, v, and w, are linearly dependent if they lie on the same plane. Huh? For the same reason this was, 3 or more, right? If you have 3 or more, it's going to be dependent. If they're in the same plane, same thing. So why does this work? Any list of 4 or more vectors, not in the same plane, are going to be linearly dependent. Turn to your neighbor this time and tell them why this is true. Okay, so just a quick reminder, if we're in 3D, you've got this one, u, and then you have a v, and then we'd have a w that's, this would be in this space. This one can be out, popping out at you, like this. Right? Could you describe any of these vectors if you have a 4th one anywhere? Could you describe this 4th one x using these? Yeah, you can, because they're in 3D, you can use a combination of them to do it. Just like you could with the 2, you can do the same thing with 3 dimensions by adding that 4th one. So I think that's kind of helpful. Just remember multiples. What you're trying to do is you're trying to get a multiple of a vector using another vector. Boom, it's going to be dependent. When for this 4 or more, it's 1 dimension higher. It's r to the n. If you have n plus 1 vectors, it's going to be what? Dependent, yeah. I think that's worth explaining a little bit. The theorem of independence has 2 parts, and I haven't talked about types of proofs yet, but this is one of the if and only if types of proofs. Whenever you see a proof that has 2 arrows, one going this way and one going that way, that means you have to prove it both ways. You have to use this as the condition to prove this, and this is the condition to prove that. So this is you have to do this proof in 2 parts, which is annoying because it's more work, but it's kind of nice too. So this says that a list of vectors is linearly dependent if one of the vectors is a linear combination of all the other vectors. So first of all, we're going to say the vectors V are linearly dependent. That's what we're assuming. So if they're dependent, C1, V1, C2, V2, C3, V3 equals 0. What does this mean? The way it's written. That's going to be independent, the way it's written. Do you have this on your slide? Yeah, so just write them in with me. I was going to reveal. Does that help if I do a reveal so you don't see it all at once? No. So I think I'd say we'll just do it this way. It's a little easier to look at. Okay, so what I do here is I have C1, V1. This is just a linear independent situation where Ci are not all 0. Ci is not equal to 0 for any of those. Okay, then what I'm going to do is I'm going to call this CIVI. See, what did they do? They added that in there, I think. So x1 times 1, 0, 0, plus x2 times 1, 1, 0, plus x3, nope, x3 times 1, 1, 1 is, we're looking at a combination that gets you 0, 0, 0. For any linearly independent, yeah. When I multiply these through, notice that I get x1, 0, 0, plus x2, x2, 0, plus x3, 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 0, 0, 0. Anything good happening here? What's x3 equal to? 0. So if x3 is 0, what's x2 equal to? If x2 and x3 are 0, what does that mean? x1 equals 0, because x1 plus x2 plus x3 equals 0, and x2 plus x3 equals 0, but we already said x3 was 0, so this cascades into a slurry of zeroness. And so what you can say then is x1 equals x2 equals x3 equals 0. Therefore, are linearly independent. Hooray. Try one more. This is a great one for an example, because I think you get it, don't you? But when you multiply through, you're going to get x minus, or x. You're going to get 0 minus x2 plus 2x3 equals 0. You're going to get x1 plus 0x2 plus 3x3 equals 0. And then you're going to get 0 minus 2x2 plus 4x3 equals 0. Want to do this the easy way or the hard way? Hard way? All right. I like your spirit. The hard way is to put this into a matrix of 0, negative 1, 2, 1, 0, 3, 0, negative 2, 4, and do an augmented matrix and do a reduced row echelon form. Well, my way is way easier. You ready to see it? Just solve what of these two sentences, what's common variable between these two? X3, right? So here's what I would do. I would say that 3x3 equals negative x1 and 4x3 equals negative 2x2, right? And up here we have 2x3 equals x2, right? So far so good? So what I would do is I would say, okay, we can eliminate a bunch of stuff here. We can say that, did I miss something? Yeah, this is positive. Good. And so this is simplified to x3 equals, or 2x3 equals x2. What do you notice about these two? What's that? Pardon? Yeah, they're the same thing. And so what's going to happen is if x3 is equal to x3, what's going to happen is you're going to get one row that's going to be all zeros. Right? Is that what happened? Yeah. And so tell me about your reduced row echelon form. What did you get, Wyatt?
1, 0, 3, 0, 0, 1, negative 0.
And then all zeros. Did we predict that here? Did we predict that was going to happen? Yes. And so that means that it's going to be dependent.
You have to put row echelon if you want to prove it like that.
Yeah, so let's do this right. So I'm going to go back here. I'm going to let x3 be equal to t. What's x2 going to be if x3 is equal to t? x2 is 2t. And what's x1? x1 is going to be negative 3t, right? So when we're setting this up, you're going to have x1, x2, x3 is equal to negative 3t, 2t, and 1t. And what can you factor out of here? T. So you're going to have x1, x2, x3. You can get that t times negative 3 to 1, where t is an element of the reals. And what does that mean? Yeah, it's not one trivial answer. This would be therefore not independent, or just say dependent. Therefore, linearly dependent. doing? Doing okay? That's perfect. I was going to start the next section, but we're fine. This one, I'm going to just give you a clue. You're going to have to do a Gaussian on it. Not too much. But you're going to have to do a Gaussian. Good practice. That is going to be your homework. Number 3, I want to do this one with you to show you that these are the easiest things ever. If U and V are any two vectors in Rn, show that the following vectors are linear dependent. And what you're going to do is find a combination for each that works, that makes it dependent. Okay? So for example, A, you're going to have U plus V plus V equals 0. So you need some kind of a what constants could we put in here to make this true? And it's an infinite number, by the way. Cameron, give me a number for this V.
-1.
Oh, I like it. Then what should this one be? Close. You'd want this to be 1. And I was thinking, oh, make this 3 and then make this 2, but -2, but it doesn't quite work. You don't know what U is. But we want these to cancel out to be 0. And then what constant can I put in front of this one? 0. And now I've got a combination that makes it dependent. Yes?
So we can't have 2, right?
Well, in this problem, they're just trying to show that there is a possibility of them being linearly dependent. You try. Yeah. You're going to do that with these. See if you can come up with some for those two. And then, would you do me a favor? Do 4. And don't do 5. And then 6 only if you dare. Okay, I'm going to double dare you to do this one. And don't do 5, but 4, 3, and I think it was 2, wasn't it? Yeah. Those are fun ones. Tomorrow we'll do basis.